In example 5, we are required to analyze a doubly reinforced section as shown in figure 5b. In example 3, we did analyze a singly reinforced beam, which is over reinforced section with 6 normal ductile 28mm bars as shown here. We have already done in example 3, and we saw that this beam was over reinforced and it had a brittle failure or the compression failure with KU value 0.57. So it is the same beam that we are analyzing, except that we have added 3 N28 bars in the compression side as well. The compression side bars are shown here with the effective cover in the compression side DSC is 50mm as shown in the figure. Rest of all the dimensions for the beam are exactly the same, and we are required to draw the strain, stress and force profile for this doubly reinforced concrete beam, and we need to find the flexural moment capacity MU and the design moment capacity for this beam, and also we have to compare the so first we draw the stress, strain and force profile for the doubly reinforced section. So this is the strain profile. As you can see, epsilon C is 0.003, epsilon ST is the strain in the tensile steel, and one extra thing that we have is this is the strain in the compression steel, which is denoted as epsilon SC. Now drawing the stress profile. This is the stress profile as we already know. Only thing extra that we will have is there will be a stress in this compression steel level as well, which we can denote as sigma SC. Now drawing the force profile. As you can see, T is the tension force taken by the steel, CC is the compression force taken by the concrete, and CT is the compression force taken by the steel in compression. So we have 3 forces in here. So the area of steel in compression. Area of steel in compression is denoted by ASC, and we have 3 N28 bars. So the area is 1847.25 millimeters square. Similarly, the area of steel in tension. Area of steel in tension is denoted by AST, and we have 6 N28 bars in tension side. So the total area is 694.5 millimeters square. Now when we have a doubly reinforced section, most likely that the tension steel will yield because we are strengthening the compression side with the compression reinforcement. So most likely this tension steel will yield, and usually the compression steel doesn't yield. So it is better to start with that assumption that the tension steel yields and the compression steel doesn't yield if it is doubly reinforced section. Now of course we will come back and check our assumption is correct or not. So we are assuming that the tension steel yields and the compression steel doesn't yield. What it implies is that epsilon ST, the strain in the tension side, is greater than epsilon SY. That means the stress in the tension steel is equal to the yield strength, which is 500 megapascal, and the strain in the compression steel, that is epsilon SC, is less than epsilon SY. That means the steel in compression is not yielding, and that means the stress in the compression steel is not equal to FSY because it is still not yielding at this point. So what we can do is we can write down the stress in the compression steel in terms of the strain in the compression steel, that is Young's modulus multiplied by the strain in the compression steel epsilon SC. So with this assumption that the tension steel is yielding and the compression steel has not yielded yet, we can proceed and go on find KU value, and we will come back and check whether our assumption is correct or not. Few things to do before that is we have the effective depth as in example 3 as well, it is 520 to the center of the tension reinforcement, which is 90 millimeter, so it is 430 millimeter. And FC dash is 32 megapascal, so which implies alpha 2 and gamma that we have already found in example 3 as well is 0.80 and gamma is 0.89. So we know that the Young's modulus of steel is 200,000 megapascal, and the effective cover for the compression side DSC is 50 millimeter. Now to find epsilon SC, that is the strain in the compression reinforcement, we can use the similar triangles, these two similar triangles here, the small one and the bigger one, to find epsilon SC in terms of epsilon CU, that means the concrete strain. So epsilon SC divided by this height of the small triangle, that is KUD minus the effective cover DSC for the compression reinforcement, should be equal to the strain in the concrete epsilon CU divided by this whole height of KUD. So that means we can write epsilon SC, epsilon CU is 0.003 multiplied by Now for the horizontal equilibrium of the forces, the tension force should be equal to the two compressive forces. So looking at the force profile, T should be equal to Cc plus Cs. The tension force T should be equal to the compressive force taken by the concrete plus the compressive force taken by the steel in compression. So T is nothing but the area of steel in tension multiplied by, it is yielding, we are assuming that it is yielding, so we can write FSY, and the compressive force taken by the concrete is alpha 2 FC dash, exactly same as before, gamma KUD B, plus the compression force taken by the steel is area of the steel in compression multiplied by the compressive stress in steel in the compression. So we don't know what is sigma SC now, and we can express it in terms of concrete strain. So how we do that? Therefore, we can solve KU. We are writing sigma SC in terms of strain in compressive steel area of steel in tension is 3.6. Now for writing epsilon SC, we can write it in terms of concrete strain as we derived before, 0.003 concrete strain, and D is 430. Now simplifying this equation, simplifying this equation, we get a quadratic equation in Ku, and solving the quadratic equation, we can find the value of Ku. If we solve it, it comes as 0.344. Now we assume that the tensile steel is yielding and the compression steel is not yielding. We have to check whether that was true or not. So checking. So the strain in the compression, the equation that we used before. Ku is 0.344. D is 430. The strain in the compression steel comes out to be 0.002. That means it is less than the yield strength of the steel, which is 0.0025. So it means that the compression steel is not yielding, which was our assumption. That is okay. Now checking the strain in the tensile steel, epsilon st. The strain in the tensile steel comes out at 0.0057, which is greater than the yield strain of the steel, 0.0025. Hence we know that the tensile steel is yielding. And this was our assumption as well, that the tensile steel is yielding and the compression steel is not yielding, and both of our assumptions are correct. So we can proceed to find out what would be the moment capacity of our beam. So to find the nominal moment capacity of the section, so to find the nominal moment capacity of this beam, looking back to the force profile as shown here. So there are three forces: tension force in the tensile steel, compression force taken by the concrete, and the compression force taken by the steel. So we are taking the moment about Cc. We can take moment about any point of application of any forces here, but for now let's take the moment about Cc, the point of application of Cc. So that will give you mu as T multiplied by this distance, which is D minus gamma Ku d over 2, and Cs, which is also acting anti-clockwise, this distance, so which is Ku d gamma Ku d over 2 minus dsc. T is nothing but area 3694.5 by 500. Area of steel in compression, which is 1847.25 and we are writing it in terms of this steel strength, so multiplied by ES 200,000 into we already know the strain in the steel is 0.002 in compression, and the distance between the two forces is 0.89, 0.344 into 430. Calculating it, it comes out to be 684.4 kilonewton meter. So our nominal moment capacity for this doubly reinforced concrete beam is 684.4 kilonewton meter, and phi for this beam is, using again table 2.2.2, it is 1.24 minus 13 divided by 12 KU, which comes out to be 0.85 again. Therefore, the design moment capacity phi MU is that comes out as 581.7 kilonewton meter. So for the doubly reinforced section, your design capacity is 581.7 kilonewton per meter. Now comparing this with the example 3 which we did, it has the same amount of tension reinforcement except that it didn't have the compression reinforcement. We found out that the doubly reinforced beam in example 5, KU is 0.36, which is less than 0.57, which we saw in example 3. That means the doubly reinforced section is ductile, whereas the example 3, it was a brittle compression failure mode, whereas this example 5, it fails in the tension failure mode. So that means compared to example number 3, the failure mode was compression failure mode. By adding the compression reinforcement in example 5, we have changed the compression failure mode to ductile tension failure mode.